Hey everyone, welcome back, and thank you for joining us again in our next discussion of statistics. Heading into our discussion then, we're actually changing gears a little bit here, as we're going to discuss non-parametric statistics. Now to be clear, up to this point, the inferential statistics that we have performed have been based on parametric statistical procedures. Well, this means that we had to meet requirements about the distribution of the random variables. That is, parametric statistical procedures are conducted under the assumption that the underlying distribution of the data belongs to some parametric family of distributions, such as our normal distribution, t-distribution, or chi-squared distribution that we've been working with all along. The procedures that we've been using thus far have been parametric statistical procedures because all of the requirements were always met. However, what if the requirements are not met? That means we'd have to use non-parametric statistical procedures. Well, non-parametric statistical procedures are procedures that make no assumption about the underlying distribution of the data. Since they do not require that the population belong to any particular parametric family of distributions, they're often referred to as distribution-free procedures. To summarize, parametric procedures are based on the underlying probability distribution of the population and its parameters, while non-parametric procedures are not based on any underlying probability distribution. Well, this does create some advantages and disadvantages for non-parametric procedures. Some advantages would be that most non-parametric procedures have very few requirements, and the computations are typically fairly easy. Some disadvantages, though, are that non-parametric procedures are typically less efficient than parametric procedures, and they often discard useful information. And since they discard useful information, they're typically viewed as less powerful. Well, continuing our conversation then, we're going to get into some inferences about measures of central tendency. But first, we previously introduced a parametric technique that is used to test hypotheses regarding a population mean. To test these hypotheses, we required that either the population be normal, if we had a small sample size, or the sample size had to be large, or it was greater than or equal to 30. If the requirements are not satisfied, we can use non-parametric procedures to test hypotheses regarding the central tendency of the population. These non-parametric procedures make inferences regarding the median rather than the mean. In this section, we're going to discuss a one-sample sign test as we conduct tests about the median of a population. So jumping right into our quick discussion example, suppose we have the following set of data, and suppose we wanted to test the hypothesis that the median is not equal to 10. Well, to use the sign test, we need to convert all observations less than 10 to minus signs, and all observations greater than 10 to plus signs, and we ignore any observations that are equal to 10. Looking at our data, we've got the values 5, 6, 7, 8, and 9 that are less than 10, and that means those would be our minuses. So that means we would have 5 minuses. And since our data is in ascending order, we can go to the other side of 10, and we've got 11, 12, 13, 14, and 15 that are all values greater than 10, which means we've got 5 pluses as well. Now remember, we need to ignore any observations that are equal to 10, and of course we have one value of 10 itself. Ignoring that value and instead just looking at the pluses and minuses, that means our sample size is 10, meaning we have 5 minuses, 5 pluses, so our sample size is 10. Now remember, the median lies in the middle of the ordered data, so ignoring all values equal to the median, we should expect half of the observations to lie below the median, and half of the observations to lie above the median. Therefore, if the null hypothesis were true and m is 10, then we should have an even number of pluses and minuses. If there are a significant difference in the number of pluses and minuses, then we will have evidence to reject the null hypothesis. Now suppose that we have much more pluses than minuses. This would indicate that the actual median m is greater than the assumed median, which in our example was 10. However, what if we have much more minuses than pluses? This would indicate that the actual median m is less than the assumed median, which again was 10. Now there will be differences in our procedures depending on the size of n. If n is less than or equal to 25, this will be a small sample case, and if n is greater than 25, we're going to consider this a large sample case. But for now, we're only going to address the small sample case. Moving to our steps to conduct a one-sample sign test where we have a small sample case. The first thing we need to do, of course, would be to determine the null and alternative hypotheses. Hopefully these feel familiar. The change now is that we're conducting our test about the median value. Step 2 would be to select a level of significance, which we know is alpha, but of course that's typically determined by the problem. And the very different part would be how we go about finding the test statistic. Our test statistic is going to be the value of k. But k changes depending on the type of test we're conducting. Well, to find k, we first need to go to our data and assign minus signs and plus signs like we did with our previous example. And these would be based on the value of the median stated in our null hypothesis. Then the value of k is based on what type of test we're conducting. If we're conducting a two-tailed test, our test statistic k will be the smaller of the number of minus signs or plus signs. Now if we have a left-tailed test, our test statistic k will be the number of plus signs. It's kind of counterintuitive since we have a left-tailed test, so we're thinking less than, while our test statistic k ends up being the number of plus signs. However, with similar logic, a right-tailed test means that our test statistic k will be the number of minus signs. Once we have our value of k, we can find the p-value using the binom CDF function. Make sure we're careful here of our input. We use binom CDF, and then we input our sample size. And remember that our sample size n is the total number of minus signs and plus signs, where we have to be careful to ignore any data that matches the value of the median stated in our null hypothesis. Making sure we're careful with that, our probability of success is a 0.5, and our value of k is determined by what type of test we're conducting. And as always, once we have our p-value, we can state our conclusion, where for one more time we know that if the p-value is less than alpha, we get to reject the null hypothesis. Jumping into our example then, we're told the website Zillow.com allows us to research real estate listings. One feature of the site is called the Z-estimate, or Zestimate if that makes you happier in your heart. And this Z-estimate represents the price Zillow believes the property should sell for. If the Z-estimate is accurate, the median difference between the actual selling price and the Z-estimate should be 0. The following data represent the difference between the actual selling price and the Z-estimate for a random sample of 10 real estate transactions. Do the data suggest that the Z-estimate is inaccurate? We're told to use the alpha equal to a 0.05 level of significance. Well, first, before we get into the hypothesis test, we need to make sure we're okay with the little bit of trickery used to ask this question. It's a bit of an indirect way to ask the question to conduct a hypothesis test because we're asked, do the data suggest the Z-estimate is inaccurate? Well, we were told if the Z-estimate is accurate, then the median difference between the selling price and the Z-estimate should be 0. So that's what allows us to realize we need to conduct a hypothesis test about the median, and our alternative hypothesis, since we're testing if the Z-estimate is inaccurate, should be that the median is not equal to 0. That is, our null hypothesis would be that the median is equal to 0, and our alternative hypothesis would be that the median is not equal to 0. So we've got ourselves a two-tailed test about the median. Well, one thing that makes us happy about this test is that the value of the median in the null hypothesis is 0. So that makes it a bit easier to see whether each piece of data is above or below the median. Well, that means the next thing we need to do would be to count up our number of minuses versus our number of pluses. And of course, we need to keep in mind that our null hypothesis states that the median is 0. Well, looking at our data, again, that makes us a bit happy. The number of minuses is easy to gather because all the values literally have a negative sign. So that means we ended up with 7 minuses in our data set. And counting up our number of pluses, all the positive values in our data set, it looks like we end up with 3 pluses. And remember, since we're conducting a two-tailed test, that means we have our test statistic, and that's the smaller of those two values, the minuses and pluses, which means our test statistic k is equal to 3. And now that we have our value of k, we need to find our p-value, which we know uses the binom CDF function. And in that function, we need to input n, 0.5, k. Well, making sure we're careful to have the correct value for our sample size, remember n is equal to the number of minuses plus the number of pluses. So we end up with 7 plus 3 gives us a sample size of 10. And of course, that's how many values of data we had. However, it only lined up that way because we didn't have any values of data that matched the value of our null hypothesis where the median is 0. We just have to be careful anytime that some values are ignored based on the data presented. Well, substituting our value of 10 for n and our value of 3 for k, we've got the binom CDF of 10, 0.5, 3, and that gives us a p-value of approximately 0.1719. Well, comparing that to our alpha level of a 0.05, we've got a p-value that is greater than our alpha level, so we do not get to reject H0. And that means we can state our conclusion that there is insufficient evidence to conclude that the Z-estimate is inaccurate. And we're all set with our one sample sign test. And thank you again for joining us.